Okay, welcome back. I hope you all had a good lunch without too much of artichoke. It was very enjoyable though. So before the break we were looking at parameter estimation, Bayesian parameter estimation, which is just the application of Bayes' theorem to a set of statements which are about the value of an unknown quantity. And that turns out to be that you're trying to find the posterior distribution for the unknown things given the known things. And the unknown things we usually call parameters, and the known things are the data. So I'm just going to walk you through a pretty simple example based on Poisson distributions and the story of photons arriving. And we're going to use data of counts of how many photons arrived in a certain time interval, or a set of time intervals of the same length. And from that, we're going to try and infer the value of that parameter lambda, which describes the expected value of the number of arrivals, or one other way of thinking about it is the long-term average rate of arrivals of photons. So the assumptions we need to make, we need to choose some parameters, choose some data, choose a prior distribution for the parameters, choose a sampling distribution or a likelihood for the data, and then calculate the posterior distribution, and that part will be formulaic. So the assumption here is that if we knew the value of this lambda parameter, then the distribution for the counts, the number of photons in any time interval, would be a Poisson distribution with that rate parameter lambda. So this is the assumption of the distribution for the data given the parameters. And that's going to form the likelihood in Bayes' theorem. It's going to involve the Poisson distribution. Yep, go on ahead.
Can you just tell them that all of our slides and presentations are in PDFs on the home page?
Okay. Yep. So some people have had issues compiling these PDFs of the slides, so we have PDFs put up on the webpage of the workshop, so you can go there and just get the PDFs, so you don't have to worry about installing all the LaTeX fonts or whatever was preventing it from compiling. All right, so in this example there are 3 data points or 3 observations, 3 different counts. And I'm assuming that the data set is just these 3 numbers. There were 21 photons, and then there were 14 photons in the next time interval, and then there were 22 photons in the next time interval. So our likelihood is that the Poisson distribution, which is univariate, it's one-dimensional, that applies to each of these 3 x's. But we need to write down our sampling distribution as a joint distribution for all of the data. So the distribution for x1, that first count, x2 the second count, and x3 for the third count. And what I'm going to assume is a very standard assumption that applies in many cases, which is called conditional independence. And that means that when I write down my likelihood or my sampling distribution, I can just write it as the product of something for data point 1 times something for data point 2 times something for data point 3, and those 3 things are all independent. So we're not assuming that x2 has something to do with x1, except that they both depend on lambda. So the likelihood function is the Poisson equation producted together 3 times, once for each of the 3 data points. And again, we can think of that 2 ways. If you knew the value of lambda, you could plug it in, and then this would give you the 3-dimensional joint probability distribution for the x's. But once the x's are known, if you plug those in, then as a function of lambda, this is the likelihood function, and that's the thing that gets multiplied by the prior distribution to give you the posterior distribution. So here's what our Bayes' theorem would look like in this specific case. We're looking for the posterior distribution of the lambda given the x's, and that's equal to the prior distribution for lambda times the likelihood function divided by the marginal likelihood. So we've defined one of the inputs already. We've defined what this thing is, this second term in the numerator, and our other input that we need is the prior for lambda, and remember the marginal likelihood just comes out, you have to compute it, but it's not like an extra independent input that you need. It's not an assumption that you need to make. It's implied by these two things and the data. So to choose a prior for lambda, we need to model how uncertain we were about lambda before getting the x's. So basically, how intense might an X-ray source be? And it depends on lots of things. You might be in a situation where you virtually have no idea, or you might be in a situation where you already know quite a lot about the source that you care about. And in those different situations, you'll want to do different things to choose a prior distribution. You might want to choose a Gaussian or something, or a gamma distribution, say, if you already know a lot about the value of lambda. I'm going to show you an assumption which is common in situations like this, which is a certain prior which is called various things. I call it a log uniform prior. And that's by analogy with the log normal distribution, if anyone knows that. And you also see it sometimes in the literature called a Jeffreys prior. And I think that is not the right thing to call it, because the Jeffreys prior is also something else, and we need to keep those two definitions distinct. But a log uniform prior has an interesting property which makes it really useful for astronomy. And one of the things that happens in astronomy, and one of the things that astronomers get teased about, is that they have to put the error bars in the exponent. It's like really hard to measure stuff. You consider it really good if you know the answer to within half an order of magnitude. And the log uniform prior is kind of like, it's a distribution that's useful for astronomers to say they don't even know the order of magnitude. And there's a few ways of thinking about it. One is how long is a piece of string? That's a joke. Twice the distance from the middle to one end. So that's the joke. And the implication is that the distance from the middle, so the middle to one end of a piece of string is also a piece of string. So if you were so ignorant about the length of a piece of string that you had a certain prior for its length, and then you had, in some weird sense, the same prior for half its length, which doesn't seem to make sense, but it kind of does in a weird way. If you want to assign the same prior for its length as you have for 2 times its length, the thing that does that is a density that's proportional to 1 over lambda. And so it looks like, on this graph, I'll just draw it there, it looks like that. And it has this property which is called an improper prior. It's not a real distribution because you can't normalize it. If you try to do the integral from 0 to infinity of 1 over lambda, it's infinity. So you can't normalize this unless you put some lower limit and some upper limit that are finite, then you can normalize it. But there's a cavalier thing that Bayesians do, which is that the fact you can't normalize it often doesn't matter. You can just chuck it in, and because it's going to get multiplied by a likelihood function, that's going to turn it into a posterior distribution which can be normalized. And so a lot of the time you can just be cavalier and say, I'm using this. By the time you multiply it by a likelihood function, it can be normalized. And the fact that I never explicitly set any boundaries that would make this integrable doesn't matter in the end. So the reason for, or one other motivation for the shape of this prior is that it corresponds to having a uniform distribution for the log of lambda. So that's why it's called a log uniform distribution. So if I, instead of thinking about this intensity parameter lambda, if I think about the log of the lambda and then I have a uniform prior for that log, then I'm assigning the same probability to every order of magnitude of lambda. So the probability that lambda is between 1 and 10, 10 and 100, 100 and 1000, those will all be the same probability. Whereas if I had a uniform distribution for lambda, you would get this weird situation, which I'll draw on the board, which is a good argument for why a uniform distribution is sometimes not a good description of ignorance.
Can you repeat? So you mean that the probability for each order of magnitude is the same?
Yes. So if, say, it's a bit messy. I wonder if, is there some liquid to clean the board with? Doesn't seem like it. Okay. Okay. So here's what would happen if you had a uniform distribution for your prior. So I'll just call the parameter lambda. Say I'm really ignorant. That's not a very good straight line, but it is straight, let's assume. And say I go out to like 10 to the power of 20, because we're talking about the intensity of something and there's many orders of magnitude involved. If I do this, and then I say, according to this prior, what's the prior probability that lambda is greater than 10 to the power of 12, say, then I would do the integral from 10 to the power of 12 to 10 to the power of 20, and I get something that's approximately 1, or very close to 1. So if you use a uniform distribution, you're kind of saying that any interval of a certain length is equivalent in probability, and when your parameter spans several orders of magnitude, that's probably the wrong assumption. If you want your error bars to be in the exponent in some sense, or treat every order of magnitude the same, then you need this. Okay.
Also say something about how much you're not sure about the value, but you know it's not completely off here. So you kind of restrict your area in a more like reasonable way.
So the question was, does this restrict, or does it in some sense contain more information than a uniform distribution? I think you could define a way in which it does contain more information, but I wouldn't put it that way, because a uniform distribution that goes on forever is improper, and a log uniform distribution which goes on forever but only on the positive side also is improper. And so if you tried to calculate like the standard deviation or the entropy or any measure of uncertainty of these things, they'd both be infinite. Yeah. So it's a uniform distributions model. So there's this kind of weird set of literature which is about what it means to be an uninformative prior, or a prior that contains no information. And it's really comes down to, well, what do you mean by this distribution doesn't contain any information? And depending on how you define it and what symmetries you assume and things like that, sometimes it's uniform, sometimes it's the 1 over lambda, sometimes it's other things. I tend to think about like which one you should use for a given problem. The way I like to think about it is to just choose something and then compute a bunch of implications of it and make sure they're not crazy. So if I chose the uniform distribution, then I could compute that probability from it and see whether I really agree with those probabilities. Because in principle, if I'm choosing a distribution, I'm also choosing a whole set of probabilities, and I should make sure I agree with them. So I think deriving the implications is a good strategy. So here is a set of Python code, or just a little script, that solves this problem. And it's relatively similar to just the examples we had before of setting up a grid of possibilities and computing probability density functions and normalizing them. And you can plot them and all that stuff. But in this one, it's that the only difference is that instead of just defining one distribution and then plotting it, I'm defining two distributions. I'm doing the prior, which is the 1 over lambda shape. And then I'm computing the likelihood, multiplying them together and renormalizing, which is the recipe to get the posterior, and then plotting that. So I'll go through each line. So first, I'm just making a NumPy array with the data in it. So that's just 3 integers. And that just needs to be there so that we can use the data. Then I have a set of possible values for lambda, and in principle it should be continuous, and it should go from 0 to infinity, but because we're in a computer, it's going to be discrete, and I'm just going from 0.01 to 100 in small steps. So something that's going to approximate a continuum in some sense. Now the prior density, I'm going to use something that's proportional to 1 over lambda. So here I've set it equal to 1 over lambda, and then I'm normalizing it by doing the numerical integral of whatever it was when it was unnormalized, and then dividing by that. Now I said before that this is improper, the integral is infinity, but because I've put finite limits on it, here the integral is no longer infinity. So I'm kind of bringing in another assumption of some definite lower and upper limits in my prior. But they're fairly generous limits. So 0.01 to 100, so we've got 4 orders of magnitude in there, and even we should be able to get astronomy quantities to within 4 orders of magnitude. So, sorry for my digs. Okay, next I've got the likelihood function. So that's the product of 3 Poisson distributions, but the x's in the Poisson distributions are not the x's. So the x's in the Poisson distribution now are known. They're the definite values given in the data. And the lambda is the thing that's unknown. So that's the thing that is that my grid is for. So I have a grid of lambda. If you simplify this expression, this product, you get lambda to the sum of the x's times e to the minus. That's got a mistake. That xi should not be there. So in equation 10, well, I guess you can't cross that out. That xi should not be in the exponent there. Should have lambda to the xi, so the product will give lambda to the sum of the x's, and this will give e to the minus 3 lambda. And then you'll have the product of factorials in the denominator. So here I'm just evaluating that in one go instead of explicitly doing the product of 3 things. So I've got lambda to the sum of the x's times x with minus 3 lambda divided by the product of the factorials. Now there's a couple of things about this that wouldn't generalize to bigger problems. One of them is that if you have a product of a lot of factorials, you might end up with a very big number, and you might get an overflow on that number, and everything would blow up. So one way around that would be to just leave off that denominator. Don't do the division, and that would be okay, because by the time I get around to normalizing my posterior distribution, it wouldn't matter that I left out a constant factor here that doesn't vary with lambda, because our goal is to find a distribution for lambda, and anything that is a constant factor throughout the whole expression here that doesn't depend on lambda will just vanish when you do the normalization. So I could leave off that division there. I still might get overflow in these terms up here, so lambda to the power of the sum of the data. If I have like 1 million data points, that could end up being something like 20 to the power of 10 million, and that would be an overflow. So your floating point numbers wouldn't be able to go high enough, and they'd become infinity. In cases like that, it's best to work with the log of the likelihood. And then, so you work with the log of the likelihood, there'll be nice moderate numbers. And then when you go to exponentiate them again at the end to make the posterior distribution, you can shift up and down the log likelihood by a constant to get it down into normal ranges so that the exponentiation won't give an overflow. But that's not something I'll go into much detail about. It's just sometimes easier, log prior, log likelihood, and then this, instead of being a product, would be a sum, and then you just have to exp the result. Here, though, I'm not using the logs, so I've got prior times likelihood, which I've called h for no apparent reason, and then prior times likelihood is proportional to the posterior. I need to normalize it, so I've got my integral, which gives me the marginal likelihood, and then I've got the posterior density there, and you can plot it. Okay. Now I don't have a plot of what that turns out to be, but I can give you an impression of what it would look like, or you can try it yourself. So in this data, the special thing about the Poisson distribution that I raised before is that the lambda parameter determines the expected value of the x's. And so if I observe these x's being somewhere around 20 or a bit below 20, then I should probably infer lambda to be something a bit below 20. So the distribution I would get would be something that looks a bit like a gamma distribution. Actually, would be a gamma distribution if you did it analytically, but it would peak somewhere around the average of the data. That's actually the end of the parameter estimation slides, so we can move on to questions about that. So the basic format of the questions will be, there'll be questions like this one, and you can base your answers on this code. So you'll just have different data, different name of the parameters, and possibly a different range for what the parameter values might be, different prior and likelihood. But basically what you're doing is you're just constructing a vector of prior densities, a vector of likelihood values, and then just multiplying them together and renormalizing them. So sticking to one-dimensional problems here, and I'll just get up the questions.
Add something.
Yep.
Would you say that you could just get rid of that denominator altogether? Because you're renormalizing underneath anyway.
Yes,
so
you can get rid of the denominator. One thing that is a risk with doing that is if you get rid of this denominator just because nothing in it depends on lambda, so it's not going to affect the posterior, it's still going to affect the value of z, of the marginal likelihood, which is that denominator in Bayes' theorem. And that has another use in model comparison, which I'll explain later. So if you do drop constant factors out, or factors that don't depend on your parameters, that's fine if you're only if you only care about getting the posterior. And it's always fine and convenient, actually, if you're only getting the posterior. Yep. Okay. So the prior, also, it wouldn't have mattered if I didn't normalize the prior, because normalizing the posterior would have give the same result. Again, it would matter if I had an unnormalized prior. It would give me the wrong value of the marginal likelihood, which might matter for purposes I haven't gotten into. I guess the reason I did it here was just as a reminder that like 1 over x is not normalized, or 1 over lambda, sorry, is not normalized. And technically, anytime I have a probability distribution, to be ideal, I should have it normalized all the time. So that's why I did it. And also, it allowed me to discuss the impropriety again. The fact that I've chosen a finite range here makes it proper, which means you can actually normalize it. So let me just bring up the questions. Okay, the first question is discrete. So it's a parameter estimation problem where the value of the parameter only has 3 possibilities. So this is actually very similar to what we had this morning. Yep.
Sorry, just about the same question as before.
Yep.
Are there any limits on what kinds of priors you can actually write?
A limit? Any
Limits on the kinds of prior. What mathematical properties does a prior have to fulfill in order to be useful? Or
it just needs to be a probability distribution. So as long as it integrates or sums to 1 over the relevant space and is all non-negative, then it's legal. But whether it's a good model of your prior information is another question.
But you said then that before that you have used a prior that is inappropriate, and you can still use that.
Okay, so it's the reason you can use it is just that it effectively what you're doing. So if I have my prior, if I was doing this problem analytically, I'd have my posterior is proportional to prior times the likelihood. And I could leave off the denominator because all I want to do is get the shape of the dependence on lambda, which will tell me what the distribution looks like. That's if you're doing things analytically, you can often leave off the denominator. And then I write down the equation for this, and the equation for that. And technically what I should do is say that all of this is only true, so I could have a big open brace there, and say all of that is only true between some, so all of that is true between some limits of a lower limit and an upper limit, which I might call A and B. So you put some low limit and some upper limit, and it's 0 otherwise. You say that your prior is only over a certain finite range. Then you go through the calculation, you see what the shape is within that range, and then you say, well, does it actually depend on that range? If I had a wide range and then I made it wider, would that change anything? And the answer is almost always no. So what you're kind of doing is putting in limits, getting the answer within those limits, seeing that the answer doesn't depend on those limits, and then retaking the limit again. But you can just do it in a really dodgy way where you have this prior that was never normalized in the first place. I hope that made sense. Más o menos, good. Okay. So the first question is discrete. You could either do this one with the numerical methods like I had on these slides, or you can just treat it as another example that's like this morning's examples. You could just do it with pen and paper, because it doesn't really involve any distributions for which I give you the mass function or the density. Second question is very similar to the one I had in the slides, just change some numbers and things. And the third question is actually something I didn't cover in the slides. It's to do with prediction. So the way that prediction works in Bayesian inference is that you get the posterior distribution, and then because you would know how to make a prediction if you knew the parameters, you kind of do the prediction as a function of the parameters and then take another expectation of it. So it's a little bit more involved. If you want to attempt question 3 without me having taught it, then hint 1 might help you do it. But we'll see how that goes. Feel free to ask if you want me to show you how it works. Okay.